Good day and welcome back for part 4 of our discussion on differentiating logarithmic functions. In this video we are going to specifically focus in on a technique known as logarithmic differentiation. Logarithmic differentiation is an ideal technique of differentiation when you have quantities which involve multiple terms that are multiplied together, maybe divided by each other, and or involve exponents. And logarithmic differentiation really hinges upon using the key algebraic properties that we have of the natural log. That would be the natural log of a product becomes a sum of natural logs. The natural log of a quotient becomes a difference of natural logs. And if you have an exponent, say it's r, inside a natural log, you can write that as a constant out front. So let's go ahead and investigate this motivating example. If I wanted to differentiate the given function, we most definitely could use our previous properties of differentiation. It would require a double application of the product rule, a chain rule when we differentiate the first term, and a chain rule when we differentiate the second term. Instead, what we are going to do is algebraically manipulate before we differentiate. And our algebraic manipulation is going to be taking the natural log of both sides. And when we take the natural log of this right-hand side, we can break it up into 3 natural logs added together because it's a natural log of a product. And I'm just going to go ahead and do that all at once. So you have the natural log of the first term plus the natural log of the middle term plus the natural log of the third term. And the first term, I'm going to go ahead and note we have 5 and we're raising it to this power, x squared. Remember, a power inside a natural log can be made a constant out front. So at this point, we've taken a natural log of both sides and we've simplified. Following the procedure we've outlined below, the next thing we are going to do is differentiate implicitly with the hope of finding dy dx and isolating it. So we want to differentiate both sides with respect to x. Note on the left-hand side what we have is an implicit derivative. We're differentiating y with respect to x. And our general rule of thumb from Calculus 1 is we differentiate that function natural log of y precisely as we would like to, 1 over y. And because it's implicit, we multiply it by dy dx. Then we work our way across the right-hand side, just going from left to right, differentiating term by term. To differentiate x squared times the constant natural log of 5, we would have the constant natural log of 5 times 2x. So I will write that as 2 natural log of 5 times x. Then we can use a chain rule to differentiate natural log of x plus 1. We differentiate the outside function, 1 over, evaluate it at the inside function, and we multiply it by the derivative of the inside function. And then the same thing with the third term. By the chain rule, we differentiate the outside, evaluate at the inside, multiply by the derivative of the inside. And I still have 2 derivatives I need to take on the right-hand side. So let's go ahead and take care of those. We have the 2 natural log of 5x plus 1 over the natural log of x plus 1. And when we differentiate the natural log of x plus 1, this is a chain rule problem. We differentiate the outside, evaluate at the inside, multiply by the derivative of the inside function. So the 1 is the derivative of x plus 1. Continuing on, we have the 1 over tangent plus the derivative of tangent, which is secant squared. So we've now completed all of our derivatives, and what remains is to isolate or solve for dy dx. And if I want to leave just a dy dx on the left, I need to multiply both sides by y. And it's tempting, maybe in our first example, to leave your solution in this form. But note, we're asked to differentiate a function only involving x's, so our differentiation formula should only involve the variable x. That means we need to rewrite y as it is originally defined. So this is the simplest step if we remember to do it. Y is 5 to the power x squared, natural log x plus 1, tangent of x. Then I'm going to simply cut and paste the remaining terms down. Which is the derivative we are looking for, dy dx. And this procedure is what we refer to as logarithmic differentiation. And note once again, just to emphasize, it's ideal when you're trying to differentiate complicated functions, especially those that involve products, quotients, and powers. So let's apply this to an example that we previously would not have been able to evaluate. Let's see if we can differentiate x raised to the power x. So to begin, let me really reiterate for you, our previous formulas or techniques do not apply in this scenario. That is to say, we cannot directly differentiate x raised to the power x. The power rule does not apply. But what we can do is use logarithmic differentiation. That is to say, we can take the natural log of both sides, and once we take the natural log of the right-hand side, we can note that the exponent inside can be pulled out front. So the natural log of y is x natural log of x. So once we take natural logs and we simplify, then we differentiate both sides with respect to x. On the left-hand side, as it was minutes ago, we have an implicit derivative, 1 over y dy dx. On the right-hand side, we use a product rule. Derivative of the first times the second plus the first times the derivative of the second. Then to isolate dy dx, we multiply both sides by y. And on the right-hand side, we have the natural log of x plus 1. Note the x over x goes away. But this isn't our final answer. Remember, we always need to make sure that we rewrite in terms of that original variable. So we replace y with x to the x. Which allows us to differentiate a function we previously were unable to handle using logarithmic differentiation. But I do want to note that there is another approach that I think might actually be a bit simpler in this case. Let's just make an observation. If we have a function raised to a function, which is precisely what we have with x to the x, we can rewrite this just like we rewrote a to the x when we differentiated it. We would like to have the natural log of f of x to the g of x. The reason I say we would like to have that natural log is because g of x is a constant. We can pull that out front. But the only way we can place that natural log and preserve the equality is if we have e raised to the natural log of that quantity. And this becomes e to the g of x natural log of f of x. And once you get it into this form, this is something you can differentiate using the chain rule. So we've outlined a general approach. Let's apply it to this specific example. So note, using our work above as a template, x to the x can be rewritten as e to the x natural log of x. And that tells us that the derivative of x to the x is the derivative of e to the x natural log of x. And we can differentiate using the chain rule. We think the derivative of the outside function evaluated at the inside function multiplied by the derivative of that inside function. And note, just so that we're not recreating the wheel, e to the x natural log of x is precisely x to the x. And the derivative of x natural log of x is something that we've already computed. So natural log of x plus 1. Not that we couldn't quickly and efficiently recompute it, but we don't have to. Note, regardless of the method we use, we come up with, unsurprisingly, the same answer for the derivative. I prefer the second approach in the sense that it's more direct. I would usually save the logarithmic differentiation as kind of a last resort if I can't get anything else to work. At this point, we've seen all of the new formulas and techniques related to differentiating logarithmic equations along with logarithmic differentiation. And it's once again an ideal position for us to do some practice. So in Canvas, you can find an associated class worksheet for logarithmic differentiation. And I would encourage you to go to Canvas, find the worksheet, give yourself a significant amount of time to work through as many of the examples as you can. And then in the next video, we will summarize by going over a few of the examples, but of course you can find the typeset solutions on Canvas as well to check all of your work. If you have questions, please let me know. So stay tuned. Take care.